In this class, we will look at an example where we have an unequal number of jobs and people. So, let us look at this example where we used the rows to represent the jobs and we used the columns to represent the people. So, here we have a situation where there are 4 jobs, but there are 3 people. Now, how do we solve an assignment problem? Can we solve an assignment problem? Now, in this case, we will relax it a little bit and say that each job will go to only one person. It becomes difficult because there are an unequal number of jobs and people, but each person will get only one job is possible because there are 3 people and we now choose the 3 out of the 4 jobs that have to be given to the 3 people. So, which means one job is not going to go to anybody. Now, which job is not going to go to anybody, which 3 are going, such that the cost is minimized is the new assignment problem in a situation where there are unequal number of jobs and people. As I already mentioned, it need not be jobs and people all the time, it can be jobs and machines, it can be students and projects and so on, it can be companies and projects, companies and tasks, it could be anything, but there are unequal number of these 2 entities. First thing we do is to make an equal number of entities by creating a 4th person, an imaginary 4th person who is going to charge 0 to do each of these jobs. So, this 4 by 3 problem, 4 job 3 person problem has now been made into a 4 job 4 person problem by adding what is called a dummy column, and the cost in the dummy column is 0, which means the 4th person, who is an imaginary person, is going to charge 0 to do every job. Now, we subtract the row minimum and the column minimum. So, we subtract the row minimum for all the rows, the row minimum is 0 because every row now already has a 0. Therefore, we do only column minimum to do this subtraction. The first column, the column minimum is here. So, it becomes 2 0 3 1. Second column, the column minimum is here 1 0 5 1. Third column, the column minimum is here 0 1 7 and 4. Of course, the 4th column has all zeros. So, this is the reduced matrix after the column subtraction. We do not do row subtraction because the row minimum is already 0 for every row. Now, we start making an assignment with this 4 by 4 matrix. So, this is the matrix. So, the first row has 2 zeros, so we do not make an assignment. The second row has 3 zeros, so we do not make an assignment. The third row has only 1 0, we make the assignment, and then we cross this 0, this goes and this goes because an assignment has already been made to the 4th column. So, the other zeros become, so all the other zeros go. Now, we look at the 4th row, there is no assignable 0. Now, we look at the first column. So, the first column, so we had already made our first assignment here. The first column has only 1 0, assignable 0, so we make an assignment here, and then this 0 will go. So, this 0 will go. Now, second column does not have an assignable 0. The third column has only 1 0. So, we will make an assignment here. To do that, we again put all these assignments in the boxes. This was our first assignment, this was our second assignment, and this is our third assignment. Now, all the zeros are either assigned or crossed, but then we have only 3 assignments as against the required 4. So, we do the ticking and line drawing procedure. So, we do that, tick an unassigned row. So, the 4th row does not have an assignment, tick an unassigned row. If there is a 0, tick that column, so tick the 4th column. If there is an assignment, tick that row, tick the 3rd row. No more ticking is possible. Draw lines through unticked rows and ticked columns. So, these are the 2 unticked rows and the ticked column. There are 3 lines indicating 3 assignments, and all the zeros are covered by the lines. So, the minimum of the uncovered element is 1, which happens to be here, which happens to be here. So, theta is 1, and now redo this matrix by adding theta to the intersection elements, these 2, subtracting theta from the uncovered elements and keeping the rest of them as it is. So, we do that to get the new matrix. Now, this 2 1 0 will remain, this 0 will become 1, theta is added, 0 0 1 remains, this 0 will become 1, theta is added, 2 4 6 0, 2 4 6 0, 0 0 3 0. So, this is the reduced matrix. Now, start making assignments in this reduced matrix. So, once again the first row has only 1 0. So, make an assignment now. The second row has 2 zeros, so leave it temporarily. The third row has only 1 0, make an assignment, this 0 goes. The fourth row has 2 zeros, do not make an assignment. The first column again has 2 zeros, again has 2 zeros, so do not make an assignment. Second column has 2 zeros, do not make an assignment. No more assignments are possible. We reach the tie situation, or we reach the alternate optima situation. So, this tie has to be broken arbitrarily, and we do that. So, again to mark the assignments, this was our first assignment, this was our second assignment. Let us assume we break this arbitrarily to do this. So, this and these 2 go, and this becomes our 4th assignment. Now, the total cost will be corresponding to these, to this assignment the cost is 4, corresponding to this the cost is 6, corresponding to the third the cost is 0, corresponding to the fourth the cost is 6. So, the cost is 4 plus 6, 10 plus 0 plus 6 is 16. If we had broken it arbitrarily, instead of getting 6 plus 6, we would have got 7 plus 5, which would have given us the same 12 and the same cost, but an alternate optimum solution. Now, from this we also understand that since this was our dummy, the imaginary 4th one was the imaginary one. So, the dummy is now assigned to job number 3. So, job number 3 goes to the imaginary position, therefore, job number 3 does not go to anybody. The other 3 jobs go to the 3 persons, this, and this, or it could be this, and this. So, when you have an unequal number of jobs and people, if you have more jobs than people, then some jobs at the end will not be assigned to anybody. If you have more people than jobs, then some people will not get jobs. Now, when you have an unequal number of jobs and people, or any 2 entities, you first have to make them equal by adding corresponding dummies. A 4 row 3 person or 4 job 3 person problem will now have a 4th person, which is a column. If I had 3 jobs and 4 persons, then there will be a dummy row. The dummy row or a dummy column, sometimes more than one, will have cost equal to 0, and then solve the assignment problem till you get the optimum solution, and finally realize whether a job is not going to anybody or a person is not getting a job, depending on which one was more than the other. So, this is how you solve an assignment problem when you have an unequal number of jobs and people or an unequal number of both these tasks. Now, we have seen the assignment problem solution by actually considering 4 examples. The first was the straightforward example where the row minimum column minimum subtraction gave us a feasible solution and which was optimum. Second example, the first row minimum column minimum did not give us a feasible solution. So, we learnt the ticking and line drawing procedure through that. The third example, we got into a situation where we were not able to make assignments, zeros were available. So, we had to make arbitrary assignments which led to alternate optimum solutions. The fourth example is where we had an unequal number of jobs and people and we solved it. So, in all this we have used algorithms which involve largely addition and subtraction, and we have used algorithms which primarily work on 2 principles. If I have a matrix where all the coefficients are non-negative, if I make assignments only in 0 positions, if I get a feasible solution, then it is optimum. The way I get the 0 positions are based on subtracting the row minimum and column minimum under the premise that the solution will not change. The only place where it looks as if we deviated was when we drew those lines and then we added something to some places, we subtracted something and we kept something the same and yet said the solution to the new matrix is the same as the solution to the old matrix, and we will have to see how that happens. We also have to see that are we going to use some ideas of linear programming, are we going to use ideas from dual to solve the assignment problem, though at the moment what we seem to have done does not seem to relate directly to linear programming. Now, we will answer these 2 questions now by looking at going back and revisiting the formulation of the assignment problem and then by writing its dual. So, let us do this. So, now let us write the dual of the assignment problem. So, first we write the primal, which is let xij be equal to 1 if job I is assigned to person j and it is equal to 0 otherwise. So, we said the decision variable to the assignment problem at this point is a binary decision, it is equal to 1 or it is equal to 0, it is not a continuous variable. The objective is to minimize the total cost of assignment. So, given by summed over I, summed over j, summed over the jobs, summed over the persons, Cij, Xij. Now, the first constraint is for every job. So, for every job Xij equal to 1, for every person j summed over I. So, every person j gets only one job out of the n jobs. The second set of constraints says for every job it will go to only one person. So, the 2 important sets of constraints, each has n constraints if the assignment is a n by n problem, n jobs and n people. There are n square decision variables because xij, I equal to 1 to n, j equal to 1 to n, there are n square decision variables, there are n plus n 2n constraints. Out of these n square are 16 variables, only 4 variables will be in the solution, only 4 variables will take 1, and these 4 variables will be such that every row has 1 variable and every column has 1 variable. There are n factorial possible solutions and we want to find out the best out of the n factorial possible solutions. Now, we said that this is a binary problem. So, to relate it to linear programming, we will now change it to a continuous variable. We will assume that xij is greater than or equal to 0. Because when we actually solved the assignment problem by the method that we saw, the method that we saw is called the Hungarian algorithm. So, when we use the Hungarian algorithm, we realized that we were getting the binary assignments. So, we will make an assumption like in the transportation that solving the assignment problem as a LP would give us binary solutions, would give us 1 or 0. I have not highlighted the unimodularity property, though I mentioned it when we looked at transportation. The same thing is true with the assignment. So, if we solve it as a LP, you will still get binary values, you will get a 0 or a 1. So, we treat this variable now from a binary variable to a continuous variable. Now, the moment we treat it as a continuous variable, it becomes a linear programming problem. Objective function is linear, constraints are linear, variables are continuous, and there is an explicit non-negativity restriction on the variables. So, we can now write the dual. Now, when we write the dual, we realize that there are n square variables here, there are n constraints here, there are another n constraints here. Now, these n constraints we define n dual variables which are called ui, and then we also define another n variables which are vj. So, there are n ui's u1 to un, there are n vj's v1 to vn. There will be as many dual variables as the primal constraints. So, there are n ui's and then there are n vj's. Now, the objective function of the dual, it is a maximization problem because the primal is a minimization problem, the dual is a maximization problem. The objective function is the right hand side of the primal. So, 1 into ui plus 1 into vj. So, maximize sigma ui plus sigma vj. Now, there will be as many dual constraints as the number of primal variables. There are n square primal variables, there will be n square dual constraints, there will be n square dual constraint. So, in this example there are 4 by 4 if we take, there will be 16 dual constraints. Now, they will be of the form ui plus vj less than or equal to cij. That is because if I take a typical xij, it will appear here in the ith constraint and here in the jth constraint. So, it will take the form ui plus vj, the objective function is cij. So, ui plus vj less than or equal to cij. Maximization problem less than or equal to, because minimization problem greater than or equal to variable. So, greater than or equal to variable will result in the corresponding less than or equal to constraint in the dual, which is the maximization problem. So, ui plus vj less than or equal to cij, and there are n square or 16 such constraints. Once again, ui's and vj's are unrestricted because the primal constraints are all equations. We have already seen in our duality that a primal constraint is an equation, the corresponding dual variable will be unrestricted. What is interesting at the moment is the dual of the transportation assignment problem looks very similar to the dual of the transportation problem, except that in the transportation problem we had sigma ai ui plus bj vj, but ui plus vj less than or equal to cij is common to both the transportation and the assignment. It is also not surprising because the assignment problem is a special case of a transportation problem. We have already seen that the assignment problem is a transportation problem with an equal number of supply points and demand points, and each supply and each demand having one unit. The most important thing is this ui plus vj less than or equal to cij, and we will use this and we will show how we have actually used this. So, we have now written the dual of the assignment problem, and we will use this dual of the assignment problem to explain why and how the Hungarian algorithm is actually optimum. So, whatever we did in terms of row minimum subtraction, column minimum subtraction, drawing these lines, putting these ticks across the rows and columns, they are all related to the u's and the v's. And how they are related to the u's and the v's, and how and why the Hungarian algorithm is indeed optimum, we will see this in the next class.